Hi everybody, welcome to 10.8, and just like before I kind of wrote out notes that I would write on the board. It's helpful for me to keep my sanity when I'm running around with my kids, but I also think it's good because then I can take pictures of it after and post it, and it kind of acts as your notes. So I'm hoping the setup helps you. All right, so I'm going to do a couple videos this section. The first one's kind of like introducing you to graphing, and then we're going to get into my later videos when I have time. Will be into the actual graphs and how you do them. So after this first video, if you're like, well, what was the point of that? We don't actually know what the graphs look like or how to make them. Those are coming later. All right, so why are we doing these now? Well, as a background story, you know x squared plus y squared equals 1. That's an equation of a circle, the unit circle. Remember, that's not a function. Wouldn't pass the vertical line test, right? To graph this, remember, you need the two equations of y equals root 1 minus x squared and y equals negative root 1 minus x squared to actually draw that circle. Technically, that's what's going on, right? So we can write this equation, x squared plus y squared equals 1, using polar coordinates now that you know about that. It would be the equation r equals 1, your unit circle, another way to write it. R equals 1, that equation is a function. Think about it, because for every theta, there's only one r value. Think about that for a minute. X squared plus y squared is not a function, because for every x value, there are two y values, the positive and the negative. So let that sit with you for a minute. And let's actually investigate why this is the case and actually look at some polar graphs and how we go from trig form to polar form and what the relationships are. Why are we now doing polar equations after talking about trig? So here we go. So say we're looking at the equation r equals 2 plus 4 cosine of theta. And to put it into trig form, I want us to think of this as y equals 2 plus 4 cosine of theta. So all I did was put y where I had r. Okay, and we're going to graph it in the Cartesian plane. So we're graphing this equation here. All right, so I again have this set up for myself. In case a child runs into the room, I'm ready to go. Anyways, here's our grid. And if you think back to the unit on this section when we were graphing trig functions, questions that I would ask you are, what are the amplitude and what are the period? So hopefully you're going to tell me the amplitude from just looking at the equation would be 4. And the period, because you're not multiplying theta by anything, the period of cosine is 2 pi, so this is staying as 2 pi. All right, and remember, we restrict the domain to only go from 0 to 2 pi so that we get unique y values. All right, so this is a review. Let's think about, we want to get a quick sketch about this. I'm sorry I keep going in and out from being blurry and not, but here I am. So let's make a table for this. Actually, you don't have to make a table, but when I flip this paper over, it might help, okay? So I know if I start my theta at 0, again, the point is not to make a table, but when we go to polar form, I'm going to refer to this. So we'll do this in degrees. I know that's a little confusing, but so if theta was 0 degrees, my y value is going to be 6. Why? Because cosine of 0 is 1. 1 times 4 is 4, and 4 plus 2 is 6. So I know I have a point right here at 0, 6. And you can go through and do more and more and more, but we kind of know what this is going to look like. Pi over 2 is going to be at 2. Again, this is all old news. We've already had our test on this. Whoops. Okay, hello. Pi is going to be at negative 2. And so that's 3 pi over 2 is going to be at 2. And then 2 pi is going to be at 6. So again, we got our cosine graph. Okay. Looks something like that. All right. So you're like, what on earth does that have to do with what we are about to do? All right. So keep that in mind, what this looks like. Notice that I shouldn't actually have drawn arrows there, should I? I should have just stopped it here. We'll just make that bigger. Shouldn't be working in pen, should I? All right, so that passes the vertical line test, so it's a function. All right, and now let's go and take the same equation but look at it in polar form. So r equals 2 plus 4 cosine of theta. So instead of having y, we have an r here. And if we were, this is an example I usually do in class, if we were doing it in class, you'd be like, oh my god, this is so annoying, or maybe you think this is so annoying right now. To show you what's going on, we are restricting your domain. I know I have this written a little backwards. Usually we write theta on the left and r on the right, but bear with me. Theta is still your input. We are looking at all, again, I have this in degrees, all your values from 0 to 360. So one rotation, right, that we used on this one, we restricted the domain from 0 to 2 pi. So we're going to do the same thing over here. All right. And I'm just going to go down the line and substitute in my theta. If we were doing this in class, we would have broken up the work, but I'm not going to bore you with putting this into my calculator. So same deal, if theta was 0, you'd still get 6. I know 30 isn't, it gives us a decimal answer. Just for our sake right now, it's a square root answer, but for the sake of graphing these, I am going to write it as a decimal. You can check me on this, but you should get 5.46 when you put 30 degrees in for theta. 60 is going to give you 4. 90 degrees is going to give you 2. Again, you can double check me on all these, but for time's sake, I don't feel like you need to watch me do this. 150 is going to give you negative 1.46. 180 is negative 2. 210 is negative 1.46. 240 is 0. 270 is 2. 300 is 4. 330 is 5.46. And 360, coming back again, is 6, which technically wouldn't really be included in the domain there, but we'll have that for good measure. Okay, so here's my poorly constructed polar grid. It's really times like these I wish my printer was working at home, but desperate times call for desperate measures. So here is my beautiful polar grid that I made for ourselves. So what I'm going to do is I'm going to graph these ordered pairs here to show you what the polar graph would look like. This is not the strategy we're going to use every time. You're not going to be making a table with these amount of theta values. This is just for sake of understanding where this all comes from. Okay, so again, we kind of already talked about graphing ordered pairs, polar ordered pairs last section, and now we're putting that to good use. So your first one, 6, 0. So that means that's going to be over here, 1, 2, 3, 4, 5, 6, 0 degrees with an R of 6. Don't draw that line segment out this time because we're actually going to plot all these points and then connect them to show you the shape. At 30 degrees, we're going to be at 5.46. So right there. 60, I'm at 4. I'm probably going to screw this up here. Okay. 4. I'm going to go through and just copy these down here. And I'm going a little bit out of order. Where am I here? 300, and I'm going weird as 4. 1, 2, 3, 4. 330 is 5.46, so right there. Okay, and then I got the middle guys here. What was that at? Oh, right, the negatives. Okay, so what I just graphed here were all of your positive R's. And so let's have the conversation about 150 negative 1.46. So 150, we know is over here. 1.46, so that's a little bit like that. But then, remember, you have to go in the negative direction. You have to go in the opposite direction. So it's going to be right here. Okay? Same thing with 180. Actually, I think I already plotted that one. That was at negative 2. Oh, I didn't plot that one yet. Good. So here's 180 at 2, but I have to make that negative, so that's going to flip over here. And then your last one that I need is the 210 with an R of negative 1.46. So that's going to end up on your 30-degree one. And what was it at? 1.46? Something like that. Okay, remember this dot here is not part of it. That was me talking. So we see we have the shape, and again, in my next video, I'm going to actually tell you the names of all these things. But this is the shape of what we have here, of the polar graph. I should actually graph them in order, or connect the points in order here. And what we will be looking for are just sketches. We're not going to need this many points for your graphs, just sketches. But so that there in the purple is what your polar graph in the equation looks like. So what do I want you to take away from this? What I want you to remember here is that both the trig form and the polar form are functions. Okay, I wrote these little notes here down that I'll post later if this thing would focus. That'd be cool. Come on. Okay. So remember, like I mentioned a couple minutes ago, the trig form passes the vertical line test. In the polar form, which is what we just did right here, each value of theta with the restricted domain, not including, I technically shouldn't have that on there, has a unique R value. So every theta, actually I should, because it needs, if I didn't, it wouldn't come back around. So I should probably have that there. But every single theta for each input, remember another way to describe a function is for each input, or in this case theta, there's exactly one output. So it's a little confusing because looking at this, it doesn't so much pass a vertical line test, but remember you're not in the Cartesian plane here. So you don't have that test, but using the definition of a function that where each input has exactly one output, your polar form of this equation does define a function. So in a minute, in my next video, we will talk about the different forms of these graphs.